Okay, I hope you're not tired of Le Chatelier's principle yet, because this page is just death by practice. Let's see what we have. I'm going to take the reaction and write it over here where there's a lot of space so I can scribble all over it. This is phosphorus pentachloride plus. In our first few examples, we didn't talk about energy, but as you learned in Unit 1, we can put energy in a reaction like it's just another chemical species. And you can apply a stress to a system by heating or cooling it just like you can by adding or subtracting atoms. So let's see what we get with this. So you can take PCl5 and heat it up, and when you do, some of the molecules actually crash into each other and break, and you get PCl3 and then some loose chlorine. And in our first example, they say, what if the temperature were increased? Well, if you're adding heat, that just treat that just like a chemical. You just say, I added some more heat. The system was at equilibrium and then I got it hotter. What will the system do? Just like with any other species, the system says, well, too much heat, I'm going to use up heat. And if I'm using left side stuff, I'm going to use all the left side stuff and I'm going to be producing right side stuff. So the system will shift right. It'll use up PCl5, it'll use up heat, and it'll make phosphorus trichloride and chlorine. Not too bad, I hope. What if we added chlorine, they ask in B? Well, if our stress is adding chlorine, then the system is going to, pause the video if you want to answer it before I go, use up chlorine, use up PCl3, and if you're doing that, you're making left side stuff, so it'll produce heat and produce PCl5. Okay, I'm going to pick up the speed a little bit because I feel like you probably have this now, but if I go too fast and blow through something that you want to see in detail, please reach out to the instructor. We're around and we're happy to clear stuff up. What if we added phosphorus pentachloride? That's PCl5. If we add this, the stress is too much PCl5. The system will use up PCl5, consume heat so it'll get colder, and make PCl3 and chlorine. Question D, what if the volume were reduced? This is new. First time we talked about this. Okay, PCl5, phosphorus pentachloride, is a gas. Phosphorus trichloride is a gas. Chlorine, of course, is a gas. Heat doesn't have a state, so we leave it out of this. If you reduce the volume of a system, like it's in a container and you physically crush it and force it to get smaller, the system says, over on my left side, I have 1 mole of gas. But if I'm on my right side, that's 2 moles of gas. In other words, the system's twice as big on its right side and it's smaller on its left side. If you're crushing the system and forcing it to pack down, it will go to its smaller side. In this case, it'll shift left. So if you crush this system and compact it down, it will go to the side with fewer moles of gas. Liquids and solids do not matter when you're doing this because they're relatively incompressible. It's only gases that we care about because they're soft and squishy. So if you reduce the volume, you'll go to your side with fewer moles of gas. If you increase the volume, the system will go, good, I can expand now, and it'll go to the side with more moles of gas. And if you have a system with equal moles of gas, like 2 moles on each side, then it doesn't care about volume. Crushing it won't do anything to shift the equilibrium. But in this case, smaller volume, go to the smaller side. And finally, what if we added a catalyst? Catalysts are the classic trick question when you're doing problems like this. A catalyst doesn't do anything to your equilibrium. It doesn't push you to the left or to the right. What it does is it makes you get to your equilibrium point sooner. So pretty much anytime we ask you about what a catalyst does, the answer is nothing except you get to your equilibrium point. You get to the same equilibrium, but you get there in less time. Okay, new reaction. Bear with me. Well, sorry, I should have written this out in advance. I'm going to pause so this will save you a few seconds. Okay, welcome to the future where I'm done writing this reaction. Same stuff. They're going to say some stresses and we're going to say what happens as a result. What if we add HPO4 minus? That's this. If we add that, can you do it without drawing the arrows? What's going to happen? The system's going to go down on the right, up on the left, correct? It has to go down to cancel this stress, and if the right side goes down, the left side has to go up. So this will shift the equilibrium towards the left. If the temperature were decreased, we're sucking heat out of the system, so removing heat. What does the system do? Up, 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 down, down. It has to produce right side stuff because it's replacing the heat we stole. Therefore, the equilibrium's shifting to the right, and shift right is our short answer. What if H2SO3 were removed? That's this. If we steal H2SO3, the system will go up, up, up to make more of that stuff. In other words, it shifts to the right. And what if we add H2PO4? That's a stress here. The system will go down, down, up, up, up. So it'll shift right again. Using up reactants so that it gets rid of the excess H2PO4 and producing products as it does. Not too bad.